So students, very good morning. So I'm going to start with the discussion that we left there in the previous class. So in last discussion, we have discussed about thermodynamics, what is the meaning of thermodynamics and what is the meaning of heat and work. Then first law of thermodynamics, we have defined that it is nothing but that is related with conservation of energy. So it states that energy can neither be created nor be destroyed, only it can be converted from one form to another form. And the total energy of the universe is always constant. In other way, we can state it like that for every 4.2 joule of work, 1 calorie heat is produced. And another statement of first law of thermodynamics is that it is impossible to construct a perpetual motion machine, that is a machine which can do work without consuming energy. So if some amount of work is to be done by the system, definitely some amount of energy will be consumed from the system. If you want to restore that energy, then either it should be supplied from the outside, or in case metabolic activities are concerned, then you have to supply it in the form of food. That we have discussed. Some processes we have discussed. What is the meaning of isothermal, adiabatic, and isochoric process or isovolumetric processes? Later on, we also discussed this human metabolism and what is the relationship of human metabolism with first law of thermodynamics. And mathematical form of this first law of thermodynamics we have derived. According to mathematical form, delta E change in internal energy of the system was equal to the amount and the amount of work that is. So if this small amount of heat is supplied and a small amount of internal energy change takes place and a small amount of work is done on the system, then del Q will be equal to D plus del W. So this mathematical form we would like to make use for other derivation purposes. So later on, we also discuss this limitations of first law of thermodynamics. Students, please, your mic should be off. Please ensure that your mic is off. Still, I am having some disturbances. So, first law of thermodynamics, it was silent about the extent of conversion, and later on we discussed that how it is silent about the extent of conversion means 100% conversion of heat into mechanical work is impossible without leaving some effects elsewhere. And this is also silent about the direction of conversion means some processes they happens they takes place by themselves, whereas the others do not takes place. And it could not explain why the flow of heat from hot end to cold end uh, takes place by itself, whereas this reverse phenomena is not possible means flow of heat from cold end to hot end is not possible by itself. So next we have discussed what is the meaning of reversible processes. Those processes that takes place very or infinitesimally slowly, they are reported as reversible processes. On the other hand, those processes which takes place very fastly, they are known as irreversible processes. And we have also concluded that in case you want to obtain maximum work during the compression process or expansion process, then this compression or expansion is to be carried out reversibly. Reversibly means very slowly we have to carry out this process. So zeroth law of thermodynamics, that is not part of your syllabus, but we have made the statement that if two systems they are in thermal equilibrium with each other or thermal equilibrium with the third one, sorry, then they must be in thermal equilibrium with each other also. So two systems they are in thermal equilibrium with the third one, then definitely these two systems will also be thermal equilibrium with each other also. That is, then spontaneous, non-spontaneous processes we have covered. In spontaneous, non-spontaneous processes, we discussed two factors that are playing an important role. One is known as enthalpy factor, another is known as entropy factor. So if during a process enthalpy of the system is decreasing, it means that the process may be spontaneous, but it is not always true. Means if enthalpy is decreasing during a process, then process will be definitely spontaneous. So this statement is wrong. Similarly, if during a process entropy of the system is increasing, you can call it as a spontaneous process, but this statement is not true every time. It means that if during a process entropy of the system is increasing, then it might be non-spontaneous. So combination of these two factors, enthalpy factor and entropy factor, we decide to discuss in the form of Gibbs free energy G equal to H minus TLs and delta G equal to delta H minus TS. If the sign of this delta G is negative, then definitely all processes for which this delta G is negative will be spontaneous in nature. So now next come to this entropy. Entropy, it is nothing but it is a measure of degree of disorder or randomness. Measure of degree of disorder or randomness. Suppose you are in a class and teacher is having your class and all of you are in systematic manner. You are sitting there. Then in that situation, entropy of the class will be less. But as soon as class is over, teacher is outside the class, then all the students, they start wandering here and there. So in that situation, the entropy of the system increases. So in other words, entropy, this is nothing but it is the measure of degree of disorder or measure of degree of randomness. So what about the mathematical statement of entropy change? Suppose del Q amount of heat is absorbed by a system isothermally reversibly. So if del Q amount of heat is absorbed isothermally reversibly at a particular temperature T, then this del Q by T, that will be the change in entropy of that system. So mathematically entropy change, it is nothing but amount of heat absorbed isothermally reversibly divided by the absolute temperature at which the heat is absorbed. So this is the mathematical definition of this entropy. So now come to second law of thermodynamics. So second law of thermodynamics is a statement about which process occurs, which do not occurs. Because first law was silent, whether the process will occur or not. So in second law of thermodynamics, we will learn why certain process can occur, whereas the other process do not occur. So there are many ways to state the second law. And one way is that heat can flow spontaneously from hot object to cold object. So heat can spontaneously flow from hot object to cold object, but it will not flow spontaneously from cold object to a hot object. So that was limitation of first law of thermodynamics. But in the statement of second law of thermodynamics, initially we are making a statement that heat by itself can be made to flow from hot end to cold end or hot object to cold object, but heat by itself cannot flow or cannot flow spontaneously from cold object to hot object. The other statements of second law of thermodynamics, you can include that complete conversion of heat into mechanical work is impossible without leaving some effects elsewhere. And efficiency of a Carnot heat engine cannot be 100%. 100% means whatsoever the amount of heat you are supplying to engine, it is converting it to a total of 100% into mechanical work. So that type of engine does not exist in nature. So efficiency of a Carnot heat engine, it cannot be 100%. That is another statement. And the all spontaneous processes are thermodynamically irreversible. What does it mean? That those processes which are spontaneous in nature, then these are irreversible. Irreversible means they take place very fastly. And another statement of second law of thermodynamics is that heat cannot be made to flow from cold end to hot end by itself. Already we have discussed this statement. So these are various statements of second law of thermodynamics. Now, there is a term that unavailability of energy, or we can call it as heat death. So what is the meaning of this unavailable energy or heat death? So the consequence of second law of thermodynamics is that in any natural process, some energy becomes unavailable to do useful work, because second law says that 100% conversion of heat into mechanical work is impossible. What does it mean? If you are supplying suppose 1000 joules of energy to system, then 1000 joules of mechanical work will not be produced by that system. It means that out of 1000, suppose 200 joules of mechanical work you are having, then 800 joules will be the amount of energy that will be lost. And that amount of energy is known as unavailable energy, or this is known as heat death. So if we took at the universe at as a whole, if we think about the universe as a whole, then what will you feel? It seems that inevitable that as more and more energy is converted to unavailable form, the ability to do work anywhere will gradually vanish. So what does it mean? More and more energy is being converted into the unavailable form or heat death form. It means that the rest amount of energy is decreasing. Rest amount is energy what? the energy that have been converted into work. So this is the meaning of heat death or unavailable energy. So this meaning of this unavailable energy or heat death, this is clear to you.
Yes, sir.
Now my screen is visible.
No,
No,
sir.
sir.
Wait a moment, because it was disconnected at that time. Now let's have a look of this Gibbs Helmholtz equation. Screen is visible.
Yes,
Yes,
sir, it
sir.
is.
So Gibbs free energy G, we are defining it as H minus Ts. This is nothing but enthalpy minus the temperature and the entropy. So Gibbs free energy G, it is a combination of two terms. One is enthalpy term and another is entropy term. And with the help of G, I had already made it very clear what is the significance of G. So if delta G is negative for a process, then definitely that process will be feasible or spontaneous in nature. So we are defining G equal to H minus Ts. So G equal to H is equal to E plus PB. H is equal to E plus PB. Then G will become equal to E plus PB minus Ts. So change in the value of G, we would like to denote it by dg. So dg will be equal to de plus pdv plus vdp minus tds minus sdt. If product of two function is there, then one we are keeping as constant and we are changing the other. So like this, how many terms we will be having? We will be having a total number of 5 terms in dg. So dg is what? DE means change in internal energy plus PdV means pressure volume work plus VdP minus TdS minus SdT. So if we apply first and second law of thermodynamics, first law of thermodynamics is what? Del Q equal to dE plus PdV. So these two terms dE plus PdV, this is equal to what? Del Q. And second law says that del Q equal to TdS. Second law says del Q equal to TdS from here. If we calculate the value of del Q will be equal to what? TdS. So if we combine first and second law of thermodynamics, then this dE plus PdV, this is del Q, minus TdS, this is also del Q. So one del Q is positive, another del Q is negative. So cancellation of these two terms will be there. So dZ will become equal to VdP minus SdT. dZ will become equal to VdP minus SdT. Clear? So we have simply applied this first and second law of thermodynamics. Students, is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
If we calculate the value of change in Gibbs free energy means dg at constant pressure, then dp will become equal to 0. dp will become equal to 0 means this term vdp will be 0. So this dg at constant pressure will be become equal to minus sdt. So if we calculate the rate of change of this dg, how this dg is changing with respect to temperature, then we would like to do dg by dt. So we are differentiating it with respect to temperature. Then dg by dt at constant pressure will be equal to what? Minus s, because this dt will be there. Either you do differentiation or these dt term will be coming out in the denominator. Anyway, you can uh, understand. So this change in gas free energy per unit change in temperature, this is dg by dt, and we are keeping the pressure as constant. It comes out to be minus s. So dg1, suppose we are talking about initial and final state of our system. For initial state, suppose g1 is the internal energy. So for initial process or initial state, this will be equal to dg1 by dt at constant pressure, this is equal to minus S1. Similarly, for final state, if G2 is the Gibbs free energy for the final state, then rate of change of this dG2 with respect to temperature dt at constant pressure, it will be become equal to minus S2. Correct? So if we subtract this initial state from the final state, then we will be having dg2 minus dt minus dg1 upon dt. This will be equal to minus S2 and minus minus plus S1. And the dg2 minus g1 we will denote it like dg delta g. So this d by dt of this delta g at constant pressure, this is nothing but it is equal to minus S2 plus S1. Further, this is Gibbs Helmoltz equation. Already we have discussed this d by dt of this delta g at constant pressure. It is coming out to be minus S2 plus S1. So this d by dt of delta g at constant pressure, this will be equal to minus delta S, because S2 minus S1 is delta S. So minus common we have taken. So S2 minus S1 will be equal to delta S. Therefore, minus S2 plus S1 will be equal to minus delta S. Now we have the value of this d by dt of this delta G at constant pressure. It is coming out to be equal to minus delta S. So this delta G for this system will be equal to delta H if we substitute the value of this delta S into this equation. Delta G equal to delta H minus T delta S. So delta G will be equal to delta H plus T times of del Y del T of this delta G at constant pressure. So this is known as extended form of Gibbs Helmoltz equation, and this form has certain applications. So this form is useful in the calculation of enthalpy of a system, because delta G equal to delta H plus T times of del Y del T of this delta G at constant pressure. And if we know the free energy change at any two different temperatures, suppose we know the free energy change means delta G1 delta G2 at temperature T1 and T2, then this term will be known to us dy dt of this delta G. Then this term is known to us and this delta G is known to us, then this value of delta H can be calculated from here. Another application of this Gibbs Helmholtz equation is that heat energy and electrical energy, they are equivalent to each other, and this delta G is equal to minus NFE. I think this is well-known relationship. This is Gibbs free energy change taking place during process, how it is related with electrical energy. So this relationship holds good. So in that way, if you apply delta G equal to delta H plus T times or del by del T of this delta G at constant pressure, again we are making use of this uh, Gibbs free energy, Gibbs Helmholtz equation. So for delta G, we can put it is as minus NFE. So substitute delta G equal to minus NFE here. This is equal to delta H plus T times of d by dt of minus NFE, because we are substituting delta G equal to minus NFE at constant pressure. So minus sign we would like to take out, or throughout we are taking minus minus. Therefore, this left hand term will become positive, and on right hand side, signs of all these things will be changed. Signs of all these things will be changed means delta H will be negative, and this term is already negative, and it will become equal to positive. So this is temperature coefficient of EMF of a cell. This is rate of change of this electrical energy with respect to temperature at constant pressure. So this is temperature coefficient of EMF of cell. So this temperature coefficient of EMF of cell is known. Then we can calculate a large number of parameters, and the delta H can be calculated if E is known to us, or if delta H is known to us, then we can calculate the value of E. So this is applications of Gibbs Helmholtz equation. So now, next thing, how much time is remaining there? Just wait a moment. Okay, in your syllabus, there is a term that free energy functions. So I am going to discuss what is the meaning of free energy functions. Two free energy functions are there. So two free energy functions are there, and these free energy functions, they define the effect of entropy as well as energy work function. So one is entropy, another is work function A, and another is Gibbs free energy G. So these are two free energy functions that we have to discuss today in this class. So work function A is defined as A equal to U minus Ts. U is what? It is internal energy. You can also write it as E minus Ts or U minus Ts. And Gibbs free energy functions, we have already defined it. Gibbs free energy functions is G equal to H minus Ts. So two functions which define the effect of entropy as well as energy are known as work function A and the Gibbs free energy G. And these two functions, already we have one of them we have defined, G equal to H minus Ts. This is free energy function, and A equal to U minus Ts. This is work function. So in detail we have to discuss them. So enthalpy, internal energy, temperature, and entropy, all these are state functions. State functions means these functions depend on the state of the system and do not depend on the path by which the state have been achieved. So all these are state functions. Therefore, G and A must also be a state function. So these two functions that we have defined, G and A, these are also a state function. So you please keep this in your mind. Why G and A are state functions? Because the combination of these terms that includes in their definitions, all these are state functions. Therefore, their sum and difference will also be state function. Therefore, A will also be state function, G will also be state function, and this A is known as work function and G is known as free energy function. So we have defined A equal to U minus Ts. Suppose for one state it is A1. This work function is A1. A1 will be equal to U1 minus Ts1. Temperature is constant. For the second state, suppose it is A2. A2 is equal to U2 minus Ts2. If we subtract equation number 3 from 4, what will happen? On subtraction, we will be having A2 minus A1 on left hand side, and this U2 minus U1 minus times of T is common, and S2 minus S1. This will be the difference. And further simplification, what will happen? Delta A will be on left hand side because A2 minus A1 we are defining it as delta A, and this U2 minus U1, this is delta U, and T is common, S2 minus S1 we are keeping it as delta F. So change in value of this work function A, this is equal to change in the internal energy minus temperature times of change in the entropy. So that way we have calculated the value of change of this work function A. So delta A stands change in work function, delta U stands change in internal energy, and delta S stands change in entropy of the system. Now, from second law of thermodynamics, what is the mathematical definition of second law of thermodynamics? Change in entropy, change in entropy, delta S, this is equal to amount of heat absorbed isothermally reversibly divided by the absolute temperature at which the heat is absorbed. So delta S will be equal to Q reversible by T. So if we calculate the value of T delta S, then T delta S will become equal to Q reversible. Correct? It means that if we substitute the value of T delta S in equation number 5, then equation number 5 will become equal to delta A will be equal to delta U minus Q reversible. So conversion of 5 to 6 is quite simple. Simply we have substituted the value of this T delta S. Now from first law of thermodynamics, we have defined that change in internal energy del U of a system is equal to amount of heat given to the system plus the amount of work done on the system. If work is done on the system, then W will be positive. If work is done by the system, then work will be taken as negative. So change in internal energy Del U is always equal to Q plus W, mathematical form of first law of thermodynamics. So if I substitute this value of delta U equal to Q plus W into equation number 6, then we will be having delta A is equal to this W reversible will be equal to del U minus Q reversible, because this is equal to Q plus W is equal to del U. And if the system does work, then the sign of this work will be negative, because work done on the system is positive and work done by the system is negative. Then this minus Q reversible will be equal to del U minus Q reversible. So on comparing this equation number 6 and 8, what will happen? In 6 we are having del A is equal to U minus Q reversible.
Sir, can you please repeat the equation number 7?
Okay, just wait a minute. Up to equation number 6, I think no problem is there. We have calculated the change in this work function A, that is equal to change in internal energy minus Q reversible, correct? So leave this equation number 6,
Yes, sir.
no problem. So now come to the mathematical form of first law of thermodynamics. First law says what? Change in internal energy del U is equal to Q plus W. सो ये मैथमेटिकल फॉर्म जो है इसको हम क्या इस तरह से लिख सकते हैं कि वर्क जो है, अगर हम क्यू रिवर्सिबल लिख रहे हैं यहाँ पर, तो वर्क को भी रिवर्सिबल लिख सकते हैं. तो वर्क रिवर्सिबल लिखा हमने, क्यू रिवर्सिबल लिखा, दिस इज इक्वल टू डेल क्यू. अगर हम यहाँ से वर्क रिवर्सिबल की वैल्यू कैलकुलेट करें तो वर्क रिवर्सिबल विल बी इक्वल टू व्हाट? डेल्टा यू माइनस क्यू रिवर्सिबल. तो ये हमारे पास इक्वेशन,
Okay, sir.
वर्क रिवर्सिबल इज इक्वल टू डेल यू माइनस क्यू रिवर्सिबल. अगर अब हाँ, ये तो था कि वी आर डूइंग वर्क ऑन द सिस्टम, क्योंकि हमने ये मैथमेटिकल फॉर्म फर्स्ट लॉ की ये वाली ली है Q प्लस डब्ल्यू. सो मैंने बताया है कि जब वर्क डन ऑन द सिस्टम होगा इट विल बी पॉजिटिव, वर्क डन बाय द सिस्टम इट विल बी नेगेटिव. अब हम क्या करते हैं, इफ सिस्टम डज वर्क, इसका मतलब है Q रिवर्सिबल जो है नेगेटिव होगा. इफ सिस्टम डज वर्क देन वर्क विल बी नेगेटिव. सो अकॉर्डिंगली इक्वेशन नंबर 7 है, इट कैन बी मॉडिफाइड एज इक्वेशन नंबर 8. हमने सिंपली क्या किया है, W रिवर्सिबल का साइन चेंज किया है, एंड del u इज एज इट इज Q रिवर्सिबल माइनस साइन के साथ. अब देखिए आप इक्वेशन नंबर 6